Hello, this video is about hybrid orbitals. Their textbook starts it on page 262, and they do just an okay job, to tell you the honest truth. It's kind of complicated in the textbook, and so if you need help, please come see me. So let's kind of talk about this. Now, in the video casting, I really only have 15 minutes to talk, so I might talk kind of loud. I mean, not loud, but fast. So if you need to, please make sure to rewind and listen to me again. Here we go. Hybrid orbitals. So normally when you're making bonds, you might think to yourself that you might expect to have the number of bonds formed by an atom that be equal to the unnumbered pair of electrons. For example, if you look at chlorine here I have the electron configuration. It ends in 3p5, which means the p block has this one unpaired electron. If it has one unpaired electron, it makes sense it would make one bond. And then if you look at oxygen, it ends in 1, 2, 3, 2p4, which means you've got these two spots, two open blocks, and you might think to yourself, well, that would be two bonds, and that makes complete sense. But things get a little funny when you think about carbon. Carbon ends in p2, so you've got 1, 2, and the third one's blank, which means if you have two empty pairs, two electrons that don't have a pair in their orbital, they would want to share their electrons to kind of fill those orbitals. That would mean you'd only have two bonds, but carbon we know loves to make four bonds, so things are a little funny, and that's where hybrid orbitals come in. Okay, so looking at ethane here, this is what we're going to focus on. Here's the Vesper structure for ethane. You can see that this carbon around here has a Vesper structure of tetrahedral because it has its north, south, east, and west covered. And this carbon around here is also a tetrahedral. We're going to watch a video that kind of shows you how this works. So here's ethane. Here's its Lewis dot structure. It's got two carbons, as you can see. Both carbons tend to have a tetrahedral shape, like we just talked about. And when these carbons, they come together, they're going to overlap their orbitals. Technically, this hybrid orbital is called sp3 hybrid, which we'll cover in a second. And these bubbles will turn towards each other and overlap. So now you can see those two electrons live in the same orbital. This is called a sigma bond. We'll cover this shortly, too. We're also going to attach those hydrogens along the outside. And those have S-shaped, or spheres, and in order to make bonds there, all of those bubbles are going to overlap. So this is what your ethane molecule would kind of look like. It's got all sigma bonds, and we'll cover that. Okay, so going back to here. In order to make a bond, you have to overlap orbitals. So let's look at normal carbon here. So here's the Aufbau diagram of normal carbon. Like we talked about before, it has two unpaired electrons. It has two unpaired electrons, so you'd normally think that they'd make two bonds. But it doesn't work that way. We can see that around this carbon here we've got four bonds, and to this carbon we've got four bonds. So we've got to do things a little bit different. What happens is they form these hybrids in order to make four bonds. So let's take all of these bubbles and kind of smash them together. See, we took an S and P's, and I smashed them together to make an sp3. There's one S and three P's inside of here, just like the boxes I took before. And then I took the electrons that were in there and I spread them out. Now that I spread them out, you can see there are four unpaired electrons. Because I have four unpaired electrons, they can now make four bonds. So this is for carbon 1. That's this carbon here. If I wanted to draw the same thing for carbon 2, it would look the exact same way. I hybridized them. Hybridized state. So now if you take a look, this orbital right here could be the bond with carbon, and this orbital right here could be the other bond with carbon. So this is this bond in the middle. This orbital here is where a hydrogen bonds, and another hydrogen and a hydrogen. That might be these three hydrogens. Over here, all three of these spots are where there's a hydrogen bonding. That would be these three hydrogens. So once again, we have bonding orbitals where there's unpaired electrons, and we were able to make four unpaired electrons by hybridizing. That's kind of the main idea here. Now, anytime you're making those bonding overlaps, like the video talked about, that's a sigma bond. The symbol for sigma is this thing right here. A sigma bond means that you've got the overlap of a bond. The bubbles or orbitals are overlapping, and they're found between the nucleus, which totally makes sense. I mean, if you have a carbon here and a carbon here, their nucleus is right in the center, and the bond happens right between the two nuclei. That's what a sigma bond is. A sigma bond is any single bond that you see in there. Okay. So why do we even do these hybrid orbitals anyway? We need to be able to overlap when bonding. If you think about normal carbon would have an s orbital, and then a 2s orbital, and then the 2p orbitals. But really all you would see is stuff that are kind of sticking out. So the only parts that are able to bond are these little p orbital bubble things that are sticking out. That's normal carbon. If you do hybridized carbon, that's where I take the s's and the p's and I kind of hybridize them together. That's when it looks, whoa, they do a much better drawing here. That's what it looks like this. You can see there's so much more overlap area that we can do. If you can overlap, let's make another one, this orbital with this one, you can see it makes a lot more overlap rather than just a little piece that might be sticking out over here. Hybrid orbitals allow us to overlap orbitals, and when we overlap orbitals, we create bonds, and those bonds are where you're sharing electrons, and the more overlap you've got, the stronger the bonds. That's the big idea of why to even do this. Okay, so let's look at another one. Ethene. Ethene is the same kind of idea, but now we got a double bond. So, let's go to our video again. Here is ethene, or they can call it ethylene. That's organic compound naming that you don't have to worry about. But you can see it's the same structure. We've got 2 carbons. Let's go back. So those 2 carbons, based on the VSEPR structure, they have a trigonal planar structure, which we can see here. Trigonal planar has a different kind of hybrid. It's called sp2. We'll cover that shortly. And so if we want to hybridize them, which we did, we can then overlap really easily to make our sigma bond. But we also have these unhybridized, we're going to put hydrogen first. Let's make some more sigma bonds by putting the hydrogens over. These are the unhybridized p orbitals, and this is our pi bond that they're making on the top and the bottom. Now it's not really that you have 3 bonds, remember it's only 2 bonds, but it's like these pi bonds, this double bond kind of circles around it, it whips around in like a donut kind of shape. It keeps going round and round and round, so we kind of show both lobes of the pi orbital, although they're really just one pi bond. See, the electrons just kind of live and they zip around in a circle around the sigma bond. Okay, so let's go back. Okay, so here's normal carbon. And what I'm going to do is we're going to make it for this ethene molecule. So let's just look at 1 carbon. If you look at 1 carbon, you can see it has 1, 2, 3 domains. 3 domains around it. That's why it's trigonal planar. 3 domains. Which means I need 3 orbitals or 3 bubbles to take. So I'm going to take an S and 2 P's. 3 domains. I need 3 lines. 1, 2, and 3. I'm going to take those 3 and smash them together. 1, 2, 3. And make this sp2 hybrid. Because I took 1 S and 2 P's. So it's sp2. Which means this other bubble is up on top still. I have an unhybridized P up there hanging out. Then I'm going to take all those electrons and distribute them amongst what I just made. I still got this 1S down here. But now that I've made this hybrid carbon, I can do stuff with it. Here's a picture of what a lower looks like. Okay, so now this is the C1. This is our C2, that's this guy. You can see I did the same hybrid here as I just drew on the last slide. All of these are going to be sigma bonds. This might be the H. The electron from the H will come and hybridize, or not hybridize, but overlap with that orbital. Here's our other H, and here's a carbon bond. That's this first bond right here. Now it really doesn't matter what order. You could have put a C, H, H. It really doesn't matter. I just chose to do H's first and the C's second. This is this H, this one's this H, and this C is right here with that bond. Which leaves me this unhybridized zone up here. The unhybridized zone also has an overlap, but this electron is that double bond. The unhybridized ones will make double bonds. And double bonds are what we call, like you saw in the video, the pi bonds. Pi bonds are just basically a double or a triple bond. So if you look at what it looks like in real life, you can see the pi bonds, like we talked about, are on the top and the bottom. But really what they're doing is like zipping around in circles around the sigma bond that's in the middle. So it's not like we have two pi bonds. It's one pi bond, but we're trying to show they're moving all the time. Okay, so pi bonds, they're the ones that are found above or below the axis. So like here we have two carbons. The first bond that's made is the sigma bond. And then the second bond that's made is the pi bond. You could draw it above it, or you could draw your pi bond below it. Either way, it's a pi bond. Okay, triple bonds. Here we go. Let's try and do it without the video, sort of. Okay, so I've got my picture down here. I'm going to look at just this carbon. We're going to try to figure out what kind of hybrid are we going to make. Well, it has 1, 2. It has 2 domains, which means I need to have 2 boxes with me. 1, 2. I'm going to take these 2 boxes. 1, 2. And this will be my SP hybrid, because I took 1 S and 1 P. I still have my 1 S down here. And now I have these unhybridized P ones up here, so I'll keep them there. Distribute your electrons. I've got 4 to put in places. There we go. That's exactly what I had going on here. Let's show what it looks like with both of them. Remember, this is carbon 1, this is carbon 2. These ones right here are the sigma bonds. This is the first bond with a hydrogen. That might be those ones. And the very first, that middle bond that's inside the carbon there, that's your first bond. That's what's happening in the hybrid zone. The hybrided zone is where your sigma bonds are, your first bonds. These top spots are where you're going to have your pi bonds. Your pi bonds are the other bonds that you're having with carbon. This will be your double bond per se, and this will be your triple bond with carbon. Double one here, and triple one. So if you kind of had to draw it, what it would look like, you've got one pi bond that zips around, and then you've got the other pi bond that zips around, and they're trying to show them all at once, which makes it very confusing. But that would be our ethyne, or the triple bond. Okay, so let's kind of fill out the rest of your chart here with our hybrid. Here we've got the linear molecule, and you see it has 2 domains, which means I need an S and a P to make those 2 domains. Trigonal planar will be an sp2. 1 S, 2 P's makes a total of 3 domains. Tetrahedral will be sp3. 1, 2, 3, 4. Add up to 4 domains. These are also 4 domains, so they're going to be an sp3 hybrid, which gets us down to those tricky ones that I talked about yesterday. I was going to explain the trigonal bipyramidal. So we need sp3. Now there's no more P's, so we can't do like sp4. We got to bring in a D block. So this brings 1 S, 3 P's, and 1 D. That adds up to 5, which means my 6 will be sp3d2 hybrid. So we better look at one of those sp3ds or something about the D's. Sorry, skipping past water. You can look at it yourself if you'd like. We're going to describe this xenon tetrafluoride, which is weird because xenon doesn't usually like to make a hybrid. If you look at how many regions he has, 1, 2, 3, 4, 5, 6. That's 6 things around him, which is why he has an sp3d2 hybrid. To make 1 S, 3 P's, that's 4. 2 more D's makes 6. 6 regions. Okay, so here's xenon. Its outer energy level is its 5th energy level, so that's the picture I would draw. All the rest of them are filled below, and they're not going to do anything. And if we're doing sp3d2, I'm going to need all those boxes. An S, 3 P's, and a D2. So I'm going to take all of these boxes and put them together. That makes 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. sp3d2. 6 of those. And then I've got these 3 lines up top. 1, 2, 3. My unhybridized D's. I've got 1, 2, 3, 4, 5, 6, 7, 8 arrows to put in. 8 electrons. 4, 5, 6, 7, and 8. Don't put them in the D blocks until you have to. There we go. I've got them all in. Let's take a look at what it looks like in a happier kind of form. This is the same thing. So now if we take a look at xenon in its tetrafluoride,